So some more formulas, things we need to know to do related rate problems. Similar triangles, we use this as a device, sometimes or to reduce the number of variables in our problems, because sometimes we have too many variables to take the derivative. That's what we're going to be doing, taking the derivative implicitly. So similar triangles come in handy. And remember, we know that this, if we have a situation like this, where we have an altitude here, this big triangle, ABC, is similar to the smaller triangle, DBE, by angle. Similarity. In other words, they both have a right angle and they both share angle B, so they're similar by angle. And if they're similar, we know the ratio of the corresponding sides is the same. So AB over DB, the ratio of this large side or big triangle to small triangle, corresponding side, big triangle to small triangle, AB to DB is the same as big triangle to small triangle, AC to DE is the same thing as big triangle, BC to BE to small triangle. So the ratio of the corresponding sides is always the same, so we have an equality there. So that comes in handy when especially when we're trying to reduce the number of variables, and you'll see those in some of these examples we go over. Okay, and then volume of prisms and cylinders. The volume of a square prism or a rectangular prism is just like a box. Length times width times height. The base area would be length times width and the height. It's the same thing. So I use it's in this general form, volume equals base area times height for any prism or cylinder. We could have a triangular prism where the base is a triangle. So we could have a triangular type box where the base is a triangle, the top and the bottom is a triangle, and we've got three sides. Okay, so the volume would be base area times height for a triangular. The triangle would be a base for a triangular prism. And then for a cylinder, the base area is a circle, so the volume is base area times height, or just pi r squared h. Because the base area is pi r squared, so you can always write that out. So that's easy. Base area is a circle. Area of a circle is pi r squared, so volume equals pi r squared h. And I guess I can write over here pi r squared h. So there's your volume. Okay. And then volumes of pyramids and cones. The volume of a pyramid or cone is always just basically 1/3 base area times height. The base area times the height. Okay. And like if you think about the pyramid at the Luxor pyramid that they have over in Las Vegas, the base is a square. So the volume would be 1/3 base area times height. Okay. One of my little dogs is having a dream, so that's what's happening. Okay. And the volume of a triangular pyramid, sometimes you see triangular pyramids in Egypt, is 1/3 the base area times height. In this case, the base is also a triangle. And then for a cone is the same idea. The volume is 1/3 base area times height. And again, the base area is a circle, so the volume of a cone is 1/3 pi r squared h. So they're easy to remember like this. Okay? And then a couple other basic formulas. Area of a rectangle is just length times width. And the perimeter of a rectangle is 2 times length plus 2 times width. And these are basic formulas. We'll be using these. Okay, and let's talk about an example. And there's some good strategy in section 4.6, so make sure you read section 4.6 after this, and you'll have some good strategy, and there are some good examples. But I'm going to talk about the ladder problem. This is a traditional problem that we use in related rates, and it uses right triangles to model this out. So a ladder 6 meters tall leans against a vertical wall of a house. If the bottom of the ladder is pulled away horizontally from the house at a rate of 0.5 or 1/2 meters per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 5 meters up the wall? Now there's an interesting exploration at the end of section 4.6 where you can put these values in parametrically. I think they use a 10-foot ladder, and you can see that the rates are going to change as the top of the ladder moves down the wall. So you could take a look at that, and we may do that in class. But let's take a look at this. So the first thing we're going to do is we're going to draw a sketch. All right, and you can go back and review that if you need. So let's draw a sketch. And here's our wall, here's the floor, the ground, and here's the ladder. And the ladder is going to be sliding down. So it's going to be might be starting up here, like this, might be leaning like this, and then it might be sliding down. Okay, something like that. I should try to do that a little bit better. Might be lining up here, might be a little taller, and it's going to slide down and down, down till, at one point it's going to look like this. And you can see that the top is going to start moving slower, and then it's going to move fast at the end. All right, so the vertical position of the ladder, it's y sub t, that's going to be changing. So we could say that's as a function of time. It might start up here, and then as time goes on, it's going to end up moving down here. The same thing with the bottom of the ladder. It might start here, and as time moves, it's going to move this way. So the bottom of the ladder is also a function of time. But the ladder is always going to be the same length. So this is a constant. So when you model these, remember, don't call this r squared because it's going to always be 6. Or h squared or hypotenuse squared or whatever. Don't use a variable there because it's not going to be a variable. It's always going to be a constant. But these are varying, so what varies you use for a variable. Use a variable, I should say. What varies you use a variable. What's constant, you use a constant. So if we just related these using the Pythagorean theorem, because this is indeed a right triangle, x squared plus y squared equals 6 squared. Okay? Now in this problem they told us that the distance at the bottom of the ladder was moving away from the wall was 0.5 meters per second, and the top was moving down. And we want to know how fast it was moving down, and it's going to be changing. So we need to know when, so they tell us when y is 5. So when it's 5 feet, it's top of the bottom, when the top of the ladder is 5 feet from the bottom, we want to know how fast it's moving down, and that would be the dy dt, the rate of change with respect to time. So what we're going to do is we're just going to differentiate both sides of this implicitly with respect to t. So that's going to be, if I take the derivative, this is going to be 2x dx dt plus 2y dy dt. And that's going to equal, and what's the derivative of 36? 0. So now we have our x, our dx dt, our y dy dt, so we have 4 unknown quantities, and we have the dx dt, we're looking for this, and the dy dt. And we'll go about solving this. The thing is, we'll have to use another right triangle to find out what x is because we know what y is. But we know what dx dt is, and we're looking for dy dt. So I have to use another triangle to find out what this x is. Okay, so let's draw another triangle because we know that these things are changing. First of all, we can solve what I'm looking for. I'm looking for dy dt, so I'll just solve this for dy dt. So first of all, I'll subtract, so I get 2y dy dt equals negative 2x dx dt. And then if I divide both sides by 2, I have dy dt equals negative x over y times dx dt. Now I know what y is because we know that y is 5. I know dx dt is 0.5. So I've got negative x over x over 5, pardon me, times 0.5. Now how am I going to find, where does this x come from? Well, this ladder is moving and it's always going to form a right triangle. So at that instant when y is 5, I have a right triangle, so I'll draw it over here so you can see it. At that instant that y is 5, and my ladder is always going to be 6, can I find out what x is? Yeah, I can use the Pythagorean theorem, so I know that x squared plus 5 squared equals 6 squared. So x squared equals 36 minus 25, which is 11. So x equals the square root of 11. So now we can just put that in, and then you'll have your solution. So I hope that makes sense. Kind of ran out of room because I wasn't planning to finish this off, but I'm going to write over here. Negative 0.5 times the square root of 11 all over 5. And then you could simplify that more if you need it. All right. So that's kind of an example, and we kind of worked it all the way through. Sometimes we have just general formulas, and that's our model. So if we have voltage equals current times resistance, and we take the derivative of both sides implicitly, dv dt with respect to t, and we're always taking this with respect to t because we're dealing with related rates in terms of time. And this would be first times the derivative of the second plus the second times the derivative of the first, and then you will probably be given data that you would fill in here. Okay? So one more thing, just make sure you read 4.6 and look at examples 1 through 4, just 4a I should say. Okay? And if you look at these examples, they should pretty much give you a good idea of how to deal with these problems. And then they also have, at the very beginning or after example 1, they have a good strategy. So make sure you read the strategy on how to deal with these related rate problems. And I think that will help you.